Oh, you're snagging, you're snagging. There we go. Okay, so we have a guest. Here is Wilford. If you follow me on social media, you'll see him every day because I post up a different picture of him every day. And there's actually a book out called The Weekly Wilford that you can purchase, $23.99 or something like that on Amazon. And it's some of the best pictures of Wilford, and it includes a weekly planner for the coming year. No one has purchased a copy yet, so I don't expect you to either. But I thought I would share Wilford since he wanted to be up on my lap right just as I was about to begin filming. And I think I've talked about him before in class. So here he is. I don't know if he's going to stay. He'll probably go back down, but yet there you are, cute, looking cute on the camera. Sort of thinking, why is he talking to no one in particular? There, but yes, he sometimes gets adventurous. Let me see if I can tilt the camera down just a little bit more. So yes, there you can see, not looking particularly thrilled, but yes, he's actually not even my cat. He belongs to my former housemate, friend of mine who rented my basement for several years. And Wilford lived here when he lived here. When my friend moved away, Wilford left, but he's come back a couple of times as my friend tends to travel around a bit. And right now he's doing a semester in the West Coast. So Wilford is staying here for 3 or 4 months. And we get along pretty well most of the time, don't we, Kitty? Yes. So that's the story of Wilford. Yes, probably more than you wanted to know. And we'll see if he sticks around or not. But we're going to be on chapter 18 today. So without any further ado, let me go to the sharing of the screen here and figure out which one we're using. I have too many screens open right now. So yes, that looks like the one. Yes. Chapter 18, there we go. Earth, wind, and fire. No, air pressure and wind. You're not old enough, most of you watching this video, to remember the group called Earth, Wind, and Fire. I'm barely old enough to remember them myself. And I couldn't tell you definitively which particular songs they sang. But there were basic elements in the ancient world, and air was one of them. And air, of course, is very important in our environment because without it, we would virtually have no environment. We can look at moons, we can look at planets such as Mercury that have virtually no atmosphere and see a major difference between those that do and those that don't. And of course, on our planet, it is a necessity for life. When we are sitting here, more or less at sea level, we're a little bit here in Indiana above sea level, but not by a huge amount. We are sitting under several miles of relatively dense atmosphere and actually under several hundred miles of a total atmosphere. All of those particles pushing down on us exert a pressure. We call that barometric pressure, and we measure it by bars, how many bars are pushing down. Each bar is 14.7 pounds per square inch, which works out to 1 kilogram, which is 2.2 pounds per square centimeter. So when we're looking at the way things are structured here, you can think about, oh, there goes the cat, 15 pounds per square inch. That's probably close for us. As we go up, there's less and less and less atmosphere above us, so there's less and less pressure. That's why when people climb to the tops of mountains, when people fly in high-flying balloons and jet airlines, you need to have some kind of oxygen shifting whether it's for mountain climbers, they often train themselves to be able to withstand that. Most of us who travel in planes actually count on the plane being pressurized. So we measure that in different ways, or differently depending upon where we are on the planet. If we are at sea level, that's our basic measurement, 14.7 pounds per square inch. Notice as we go up in the atmosphere, we have fewer and fewer particles. And we've talked about that a bit in the past along the way. But it's pretty uniform throughout the entire planet. So you're not going to get a huge discrepancy of this pressure between what's happening at the equator and what's happening at the poles and what's happening here in Indiana. The real difference comes from your altitude. If you're in Denver, you have less pressure than you have here in Indiana. Why is that? Well, think about the stadium name in Denver, Mile High Stadium. That's because it's a mile above sea level. We are not a mile above sea level. We're not even a quarter of a mile above sea level here in Indiana. So we have different things that we can use to measure. One of them is sort of a mercury level kind of thing. This was invented in the 1600s, and it's one of those interesting things where the mercury is in sort of the really old ones that I've seen is sort of in a puddle, and you stick a vacuum tube into it, and the pressure pushes down on the mercury and pushes it up into the tube. And one of the things Torricelli and others noticed very early is that when you're at the tops of mountains, say in Switzerland, or the south of France, or the north of Italy, which is the area that this was being experimented in, you have less pressure. You have less of the mercury going up the tube than you do if you're down at sea level at the Mediterranean. We do have some ways of measuring it without liquid, without mercury, because mercury is a little bit dangerous to work with in different ways. So if you ever have a thermometer that has mercury in it and it breaks, avoid the mercury. They sort of figured that out. We can measure it continuously, or we can take one-off measurements along the way. But this shows, as I was mentioning before, the mercury coming up the vacuum tube, the air pressure pushing down on it below, and of course you keep the mercury in a container so that it doesn't expose, you don't get exposed to it. Here's an aneroid barometer, and one of the things that we can see here is the change pressure is being done in the sort of vacuum tube and coils that we have here. As the barometric pressure changes from higher pressure to lower pressure, we have weather changes happening. And one of the things you can see on this barometer is that we have a higher pressure when we have drier weather. We have lower pressure when we have rainy and precipitous weather along the way. It never really gets down below this, and it never really tends to get up above this very much. So the temperature range on our planet is much greater than our pressure change. Our pressure change is actually a pretty narrow band, whereas our temperature change goes wild in many ways. We can record things continuously onto paper. This is a very old kind of thing. Nobody really does this too much anymore with the advent of computers. But this is one of the ways in which we could make longer term assessments and then make longer term observations. Pressure helps us to understand how wind and air is moving. So one of the things that we see is we have pressure gradients and isobars on our maps that will help us determine where high and low pressures are. You've probably seen these on weather maps. We'll often have highs and lows. Again, low tends to be where the stormy areas are. High pressure areas tend to be less problematic in that way. And this is one of the ways in which we can use isobars. So we have sort of low pressure and high pressure areas, and where we have the wind happening, we have these wind speed symbols. And you can sort of see just by learning them, they're almost like semaphore flags. You can sort of see the direction of the wind. We all sort of have this huge cyclone idea going on here, and we have this dip here. We could sort of follow it through to the top up there. We have very low winds going down here in the Gulf of Mexico and the Pacific Ocean at this time. This is always changing. Of course, the weather is always changing. And at this point, we have some pretty high winds going on. Guess what? Right in Indiana. I didn't pick this map just because we're here in Indiana. Notice we've got our black flag, and our black flag with an auxiliary spike here and here. So we're getting 50, 60, 65 mile an hour winds in these areas here. So that's quite severe. We have a Coriolis effect, as I've mentioned this before, in terms of whether it goes in a counterclockwise or a clockwise direction. This is due to the Earth's rotation. This does not apply to pipes and to water so much. If you've ever seen that Simpsons episode where Homer goes to Australia and asks if things swirl in the other direction, the direction of the swirl of the water that comes into your sink or your toilet or your bathtub or whatever is always going to have more to do with the orientation and leveling of the pipes and the pressures of the water than it's going to have with the direction of the Earth's rotation. That is not true when we're dealing with the atmosphere, which is not physically attached to the Earth. It's held in place by gravity, but it's not physically attached in the way that a piping system, a plumbing system would be. So it is deflected by our rotation. We do have a little bit of friction as a result of this, but it only is very minor and only very near the surface. So as we have a rotation, one of the things that happens, of course, is we're rotating. If we're looking at the North Pole, if we're looking down from the North Pole, we are rotating in a counterclockwise direction. So one of the things that we see is the bend away is going to be opposite of that. So that's the Coriolis effect. That is going to have I think it's mostly apparent when we're looking at things like hurricanes. As if you watch the hurricanes, anything or cyclone, big cyclonic storms in the Pacific, and typhoons. When you look at the ones in the northern hemisphere and the southern hemisphere, they're going in opposite directions. We also have upper air winds, which are sort of higher above the troposphere, and they can get to going very quickly. And we have bands of atmosphere that are going in one direction or the other or a third direction, depending upon whether they are in the tropical zone, in the mid-latitudes, the temperate zones, or in the Arctic zones. And the jet stream is one of the best known ones here in North America. It goes from west to east. Most of our weather patterns, thus in the United States, go from west to east because they're following this jet stream. If you are flying from LA to New York, it can actually make your trip a little bit faster, and it takes less fuel to go there. So as we're looking at these, we call these geostrophic winds. We're going to have different kinds of bending effects because of the Coriolis effect. We also have the wind itself going, and then we have our pressure, which is affecting how it moves. So we've got these multiple effects that in each instance is very small, but they build up over time and distance, so that instead of just sort of having one effect, it sort of spreads out, as we can see over here. So some of the effects mean that what we have happening on the ground level will be somewhat different from what happens up above, where there's no friction. And the different effects, the Coriolis effect, the pressure gradient force, and the wind will also be shifted a little bit. And again, it's little by little by little. But if you're just a little bit off and a little bit off and a little bit off in each step along the way, eventually you're going to be out of sync. Just as if you had two stopwatches and one was 1 second slower than the other, eventually you're going to notice a bigger and a bigger and a bigger effect. And that's what happens with our upper level and surface winds along the way. We do have cyclones. Cyclones are not just tornadoes. We sometimes use that word to describe a tornado, but a cyclone is really any kind of rising air circular pattern. We can have a cyclonic effect over the entire continent. For example, an anticyclone is associated with sinking air. Cyclone has low pressure, anticyclone has high pressure in it along the way. So here you can sort of see we have a low pressure cyclone taking up half the continent. We have a high pressure anticyclone taking over half the continent over here as well. So, when we are dealing with the cyclones, we are typically getting again a counterclockwise and an inward convergence. In the southern hemisphere, we're still getting that inward stuff, but it's going in the opposite direction. Remember, north and south are going to be opposites of each other. So the more we go towards the center, the more the pressure decreases. And if you remember from our barometer a few slides back, let me go back to that here quickly. Notice low pressure means storms along the way. We are getting to the anticyclones. The wind patterns are going outwards. That is competing against the Coriolis effect. So we're going to have a clockwise happening here. And in the southern hemisphere, we have a counterclockwise way of operating. And it usually brings fairer weather because, of course, you're sort of pushing away any kinds of things that are going to be problematic. So when we're dealing with those kinds of convergences, one of the things that happens is that if things are going downward or upward, it's going to affect whether or not we're getting something from the ground going up. If it's from the ground going up, it's often going to take moisture with it as well, evaporated water. That will create clouds, that can create storms, that can create precipitation. If it's coming from above, typically not nearly as much unless it's already there, and then it dissipates rather quickly. So this is why high pressure areas with the anticyclones will be calmer and more still weather because it's sort of dissipating those kinds of forces. So part of this happens because we have an unequal surface heating on our planet. We don't get the same amount of heat from the sun because we are not flat, we are a sphere. This is yet one more example of how we know that we are a sphere. Because even if the sun is hitting the North Pole and the equator and the southern hemisphere at the same time, the angle of the sunlight, and I think we've covered this once before in our class, the angle of the sunlight is different if it's a sharper angle. If it has sort of like 90 degrees, the sun is directly overhead, that's an angle of high incidence, and that will give you the most intense, most direct heat. If it's a low in the sky appearance of the sun, like would happen at the polar regions, that's a shallow angle of incidence or a low angle of incidence, and you don't get nearly as much. But as a result, we tend to have our three areas of atmospheric heating, which I've mentioned just a moment ago. We have our tropic zone, our mid-latitude zones, and our Arctic zones. We tend to call these cells, and they tend to be pretty standard and pretty stable most of the time. When we're dealing with the area where they bound against each other, we have like the subtropical high pressure zone. This is where the tropical zone and our mid-latitudes, which is where we live here in Indiana, hit each other. So we end up with windy areas. These are great for sailing ships. These are about 30 degrees up, so about 1/3 up from the equator towards the pole. We have lots of big deserts in this area here because it's a stable and high pressure means stable area, not a lot of rain. So the Sahara Desert is here. The deserts in the American Southwest are here. Some of the deserts in China and India are affected by this as well. There's also some continental affecting that's happening there. Then we have our polar high pressure zones. Again, not a lot of rain, snow, precipitation at these areas, but again, between that and the temperate zone, we end up with a low pressure zone. So we have a lot of storms. And a lot of storms here in Indiana come from that. We get our sort of polar vortex kinds of things that happen there. So here we can see our equatorial low pattern, but then we have our trade wind areas here. Notice we've got the different spins happening depending upon whether they're north or south. We've got our subtropical high pressure area, which is going to give us the calmer areas. Then we have our bounding areas between the polar area and the, again, our mid-latitude regions that are here. So we have this big cell in the middle. We have above it and below it our mid-latitudes, and then above and below that we have our Arctic areas. So these would be our tropical areas here around the equator, our mid-latitudes, and then our polar areas. And each of them is roughly 1/3. Continents will shift things. The most obvious influence is in the northern hemisphere, where most of the land exists on our planet. Most of the southern hemisphere is ocean. Most of the northern hemisphere is land. We end up in the winter months with a lot of dry continental air. We end up in the warmer months in the summer, spring, and early fall with monsoon seasons and hurricane seasons, where the warm ocean air is forming storms that then flow over onto the continents along the way. So here we can see typical high pressure zones in January. Notice we've got a lot of calm stuff here in the southern hemisphere. It's going to be summer in the southern hemisphere in January, but we've got low pressure in here and here. There are rainforests in Africa and in South America in these areas. And then we've got our areas here, including our Icelandic low area here. So lots of cloudiness happens in Iceland in this time of year. Then we get to our July. Again, it's going to be summer in the north. It's going to be winter in the south. We've still got calmer, high pressure areas down here. Again, notice mostly we have ocean down here. Mostly we have land up here. And good old Iceland gets some clear areas here. But we can see our lows push up into the mountains here. Our lows are in the mountains over here as well. So we get lots of precipitation, lots of snow and rain in the mountain ranges that are there on both sides. So mid-latitudes, this is where we live. We have airflow that tends to be interrupted by these huge areas. We've already talked about the cyclones a bit, and one of the things that we see there is that they will create a weather pattern that Melissa is going to talk about more in chapter 19. We do have minor shifts here and there locally. If you're on the coast, you may notice you're typically getting a breeze off of the ocean most of the time. If you're in mountain and valley areas, you're going to get sort of used to the way the wind is affected by going through the valley or up and down the mountains. We get different things that happen, different wind patterns that happen off of the oceans and off of the desert areas. So these are smaller and more localized. So we're never going to get Santa Ana winds here in Indiana, for example. We're not typically going to get sea breezes here, although you can get a little bit of that if you go up to Lake Michigan and you get lake effect weather, especially lake effect snow. If you're on the east coast of a lake, a big lake, if you're over in New York State, for example, they get like feet and feet and feet of snow as the wind pattern brings the water, the H2O, which then freezes and gets dumped as snow off of the lake onto them along the way. So, and we can see a pattern that happens that changes daily depending upon whether the area is being heated by the sun or the residual heat of the ocean and the land is being used to generate the pattern in the evening. The moon doesn't really give us any heat. This shows us a sort of valley breeze versus a mountain breeze. Notice that tends to change during the day. During the day, the cool air sinks, whereas out of the atmosphere, and the valley breeze goes up. Whereas when we're in the evening, the mountain breezes will sink back down and the warm air will rise up in the middle. So when we're measuring wind, direction and speed, we will tend to direct the location where the wind is going by the compass points. So remember the compass, north, east, south, west, 360 degrees in that circle. So we will say northeast, southwest, but we'll also break it into north, northeast, south, southeast, and so on. And sometimes you'll even get it sort of to a three-letter designation. So if you give it a degree measurement, you're being much more precise. But wind often isn't quite as precise as that. And then you have the good old weather vanes. That's sort of like the thing that's at the top of the courthouse that spins, and you can tell which direction the wind is blowing. So the winds are labeled where they come from, where they're going is typically going to be the same. And prevailing winds will sometimes come from one particular direction. So we're sort of used to, in our part of the world, most weather patterns coming from the west, although sometimes it can come from the southwest or the northwest here. So wind frequency up in the northeastern United States, we can sort of see this pattern here. Most of it's coming from the west, northwest, and southwest, much less from the south, southeast, and east, a little bit from the northeast here, but that's because we have this pattern of weather that's happening off of the coast of Canada. When we come down to Australia, we can see there's a very pronounced shifting from the south, the east, and then very, very much the southeast here. Virtually no wind down under comes from the north, the west, and the southwest, this area over here. So it is quite different. We can measure the speed with an anemometer, and that is basically a kind of cupping device that you'll see spinning around. We can also use just a sort of a wind gauge. So changes in wind direction will bring changes in moisture and temperature. Those can often be associated with cyclones and anticyclones, as we've seen already. One of the better known patterns is El Nino, and this relates to how the water in the ocean, the Pacific Ocean, sort of heats up and cools down. When we have warmer than normal temperatures, it will cause a lot of changes in the atmospheric humidity and the atmospheric precipitation, and it will cause a lot of big rainstorms all along the Pacific coast, from the southern hemisphere to the northern hemisphere. Southern California is in the northern hemisphere, and it will change the weather patterns throughout most of North America. So a lot of the water will get blocked by the mountain regions in the west of the United States, but the overall climate gets changed. La Nina is triggered by colder than average temperatures. And one of the things that happens is that it will then push colder air up, but that colder air tends to go up into places like Oregon, Washington, sort of over the mountains into Canada. And one of the things that happens is we get a lot more snow and a lot more of just general precipitation, sometimes even flooding conditions in the northern plain states. So we can sort of see here the sort of the El Nino, where we have our strong current of warm water, whereas if we have our La Nina, the cooler water that's pooled up here is pushing the warmer water away from the western hemisphere. So these will affect, in smaller degrees, the weather all over the world, because the Pacific Ocean changes its various flows in minor ways, not majorly, fortunately, but in minor ways. But again, the sort of the knock-on buildup over the course of time will change the weather pattern all around the world because of the global conveyor belt in the oceans. And so we call this the Southern Oscillation that's happening here. So we can see over the course of our shifting times here how the different patterns form in terms of where it's warm and where it's colder, especially water-wise, where it's drier and where it's wetter in the atmosphere, which will give us an indication of whether or not we're going to have more storms or fewer storms, more cyclones, more hurricanes along the way. So when we're dealing with looking at our planet, you can sort of see the image behind me here. It looks like there are clouds all over the place. It looks like there are clear skies all over the place. We have low pressure and high pressure areas that are forming and deforming all the time. But there are some areas that tend to be fairly stable. The Sahara Desert, the Kalahari Desert, the Southwestern Desert in the United States, the Gobi Desert. These tend to be pretty high pressure areas almost all of the time. So they will get the occasional rainstorm, but not very much. On the other side, we have the Amazon and the Congo basins, both of those at the equator, and they have great massive rainforests. Low pressure areas, they are almost always experiencing a wet environment along the way. So these areas, these land masses, are right at the equator, and when we sort of go up from them in the northern hemisphere, we get lots and lots more land. When we go down from them into the southern hemisphere, we get less and less and less land there. So we get drier territories in the northern hemisphere because we have huge blocks of land. We also have major mountain areas, especially in North America. We have the Rocky Mountains, Sierra Nevada mountains, other mountain ranges all the way from Alaska down to Mexico. And then, of course, that continues as a smaller chain down into Central America, and then it picks up big time again in South America. But the side that's hit, that the weather patterns are hitting, tend to be very wet. The leeward slopes, the opposite slopes that aren't getting that, often will be much drier. So we can sort of see here on this side, all of the water is happening on the west coast, but it gets blocked. Notice how dry it becomes just as we get past the mountains here. The mountains are blocking things. Not a lot of mountains in this area here along the equator. Notice how wet it is. This is a rainforest. This is a rainforest. All of this in Indonesia and Southeast Asia are rainforest territories. Then we get these much drier areas. Australia, this is the Sahara Desert into the Arabian Desert. We have the deserts in China. We have desert-like territory way up into Siberia here. And that's it for chapter 18. I will see you again soon with chapter 20. But again, I hope you enjoy Melissa's rather involved presentation for chapter 19. She is a real expert at this, so she goes into a great amount of detail, and I hope you'll take advantage of that.